Hello, my name is Chirag Saxena and the topic which I will be discussing is GANs. I'm a third year student at Bennett University and my area of interest is machine learning and deep learning. Let us dive in straight into GANs. Let's start our discussion about GANs by actually discussing what GANs actually are and what they actually mean in deep learning. GANs are also known as Generative Adversarial Network are and very powerful. Let's discuss about this more. The GAN model architecture involves two submodels. One is the generator and the other one is the discriminator. The work of the generative model is to generate new realistic data that is very significantly similar to the original information or original text or image or any data type that we actually feed into the generator. What discriminator does is it actually differentiates between what the actually is real and what is fake, and it gives the loss function to the generator so that the generator can tune its hyperparameters or tune its other parameters to generate new images or other varied dataset that can again be used by the discriminator, and the cycle goes on. This provides a variety of dataset and thus improves the richness in the dataset, providing us with more variety of aspects to cover. All the images that you see in the slide, the dog, the mountains, the butterfly, and this burger are all photorealistically similar to what we gave into the input, and these all are generated by the GAN. This actually is the result for Deep GAN, which was the paper introduced in 2011. Let's move on. Now let's have a deep dive into what generator and discriminator actually are, what is their different significant functions. This image clearly shows working of the two models. We firstly provide our input to the generator. It multiplies and performs all the functions that it needs to generate. Generate the closest neighbor, or actually finds the closest neighbor of the input data in the data set that we have given to the generator, and then it uses all the information and tries to create a new image or text depending on the input that you gave to the generator. And then the output from the generator or the generated example is given to the discriminator, which differentiates between the fake and real data and provides the generator the loss function. This loss function is again used by the generator to either to carry out further the next iteration or tune this hyperparameters only to generate a new example, which again the discriminator use, and the cycle goes on until we actually cover a variety of data set or the input or the class that you give the GAN to cover. This is how the GANs actually work. There have been a lot of research in the prospect where we remove the real example from the discriminator input and give some ground truth values to the discriminator to change the hyper parameters or the loss function so that the generator can touch a new variety of dataset. So yeah, a lot of research has been going on to this. Same, the GAN model arrives two submodels, a generator model and the discriminator model, as we discussed. The following image shows the actual GAN and discriminator in working. So we give a d-dimensional noise vector to the generator network. The dimensional has a noise so that as I said, the variety can be changed for the dataset. So the generator discovers some fake images. Discriminator model gives are the similarities or what are the differentiates between the real image and the fake image, and predicts a loss function or the labels for the generator to work upon in the next iteration. Yeah, let's come on to the power of GANs. What actually can GANs do and what actually can GANs provide to us? All the images that you see in this slide are actually generated by GANs, and all these people do not exist in reality. There is a data called known as FFHQ dataset that we will see in the next slide. The whole dataset is actually generated by GANs, and it contains 1.2k pictures of people that do not exist, but the model has generated. As I said, generated adversarial network can generate near photorealistic images. You cannot much differentiate between the generated image and the GAN and the actual images using that discriminator. The discriminator function is actually very powerful, and its power has been increasing in recent years through the research and various aspects that we give it to. So yeah, but there are some problems with GANs. GANs face with mode collapse problems, with generating being too powerful, as I said, or the diversity of the data set is reduced, which let's discuss further. All are these example again. All these are an example of what you see here. This is the input, and we check the variety of dataset on different aspects. So first, the gender of the input was changed. As you can see here, this male was turned into a female, and again gave us these results. Again, for when we change the age of the input side, this is given. We change the gender again, then we change the age to old age. So these are the results. The GANs works like this. Working aside, GANs try to find and locate a local clustering of images, find their nearest neighbors, overlap them, and then decide what to choose and what to forget, and then generate the new images or the image that we talked about. This is an example of clustering. So as you can see in the A image, first of all, the GANs try to find all the closest neighbor of the image that it is currently iterating on. So you can see here the dogs, that all these dogs are the closest neighbors for the current iteration. And then this image goes through this is the generator model. These are all the discriminator model. Discriminator model, as we discussed, it gives two calls, either the image is fake or real, and provides a loss function again to the discriminator. And then the generator can decide whether to change its hyperparameters more or less and generate new images for the sample. Moving on to the benefits of GANs, as we discussed, GANs required no label data. As you know that labeling a data is a very compute as well as expensive task. So as GANs are unsupervised, they don't need any labeled data. GANs produce sharp images. All the adversarial networks till now don't produce such sharp images like GANs produce. Big GAN and IC GANs have been a major improvement in sharpness of images that are provided by GAN. Coming on to the benefits of GANs again, GANs can be used for data generation. We can use the datasets to generate a lot more datasets similar to the current dataset that we are using. GANs provide a lot of detail about your dataset as it iterates through each and every cluster of that image and finds its nearest neighbors. So you can actually use these nearest information to train your other models using GANs as the first layer, and then using some other layer using the information provided by GANs to train your other models. Coming on to the problems with GANs, GANs actually suffer from vanishing gradient problem. As we discussed, generators are very powerful, the discriminators are very powerful, so they sometimes reduce the fake and real images differentiation so small that there is no loss function, and the gradients try to become small and actually vanishes. So there is not much movement for generator left. GANs actually also suffer from mode collapse. As GANs need a variety of data set, they may less got in the discriminator with happy with one kind of results. So the variety of data set may sometimes get lost and leads to overfitting. GANs can also fail to converge, and that's why we add some noise or some augmentation in the initial input to our model, so they don't converge, they don't fail to converge and actually give us some outputs. These are some applications for GANs. GANs can actually produce high quality images. They can provide us with more dataset like FFHQ. They can help us in image to image translation. They can help us in text to text image translation. Text to image translation is nothing that if we write like tree on a bird. So GANs can actually provide us that image, and image to image translation. You can see the image. We can produce an image with night effect using the daylight photograph. So yeah, we can blend two photographs using GANs. Moving forward, these are some experimentation that were done on GANs using ICGAN. So these are the results for the same. We actually used data. We actually used ImageNet and Copus2 dataset and trained our image and trained our GAN model on 50K image. The model is known as ICGAN and uses ResNet pre-trained model for actual differentiation. These are the results that we got from the model. So if like I said, we can use text to image translation. So we gave a image of one dog and added golden retriever with it. So what GAN did was it actually mixed the two images and gave us these outputs. We actually then added the golden retriever keyword with this dog, and it firstly found the closest neighbor and then provided us with these outputs. So these are all the outputs that we got for the experimentation. Moving forward, at last, summarizing the PPT, GANs are very powerful. They can generate new dataset. A lot of research has been going on through GANs, reducing the power of a discriminator, so that generator can actually look for a variety of dataset and produce a diverse images. GANs are computationally expensive, so you should consider before you use them. You should actually go through your case test before you use GANs. These are some collaborations that we found. These are again the results for ICGAN model. This is our input. This is our input, and these are all the outputs or the closest neighbor that the this compares the ICGAN model with 6 neural networks, and these are the actual results from the ICGAN model. Though GANs are powerful, they may sometimes, as we discussed, fail to converge. This is a result when the GANs fail to converge. This is the result that we got when we mixed the image for McDonald and Jack O'Lantern. So these are all the scary stuff that we got, and this actually is due to the result that the discriminator is happy with the result and keeps on sending the images okay, and the loss function keeps on reducing, and again the vanishing gradient picture comes into the picture and giving us this as the output. These are all the resources that were used in the PPT, and all the images and all the results were used from GAN paper that is also linked there. That's all on topic of GANs. Thank you.